Hello guys, in this video we're going to discuss about electrolysis, the last part of electrochemistry. What is electrolysis? In previous lesson we learned that the electrolytic cell means it is non-spontaneous. The chemical reaction of electrolytic cells are non-spontaneous. We should supply electrical energy for the reaction. Electrolysis is conducting a non-spontaneous chemical reaction using electrical energy from the outside. Let's write it down. What is electrolysis? Electrolysis means conducting a non-spontaneous chemical reaction using electrical energy from external source is called as electrolysis. In electrolysis, the electrode that is connected to positive terminal of the external source of electricity is positive electrode, which is anode, and the electrode which is connected to negative terminal of the electric source is negative electrode, which is cathode. Let's write it down. Electrode connected to positive terminal. Here the electrode connected to negative terminal of external source. If it's connected to positive terminal, it will be positive electrode. And if it's connected to negative terminal, it will be negative electrode. And the positive electrode is known as anode. And the negative electrode is known as cathode. Here the oxidation reaction and reduction reaction is opposite to galvanic cell. In galvanic cell, in an reduction occurs. In cathode, oxidation occurs. But here in electrolysis, in anode, oxidation occurs. In cathode, reduction occurs. The first part of electrolysis is electrolysis of water. Electrolysis of water. Electrolysis of water is not spontaneous at standard temperature and pressure. Therefore, in order to electrolyze water, we should supply external electrical energy. Let's write it down, not non-spontaneous in standard temperature and pressure. Therefore, we need to supply external electrical energy. And when the external electrical energy is supplied, electrolysis of water occurs. Now let's look at the experimental setup of electrolysis of water. This is the setup of electrolysis of water, and this green color is the wire, conducting wire, which is connected to a electrical source. And this is a solution which is sulfuric acid H2SO4, diluted H2SO4 solution. Here there will be O2 gas produced, and here it will be H2 gas. And these are boiling tubes. These were the boiling tubes, and this is a stopper, and these are, both of these are platinum wires. Platinum wire. Matrix terminals should be interchanged, and this is plus terminal, and this is minus terminal. This is positive terminal, and this is negative terminal. The main ionic species of pure water is H plus and OH minus, H plus ions and OH minus ions. The dilute H2SO4 is added to water to enrich H plus in the solution. When H2SO4 added, the H plus concentration will increase. Increasing in H plus concentration facilitates conduction of electricity. Let's note it down. H2SO4 is added, diluted H2SO4 is added to H2O to increase H plus ions. Now let's look at the reactions in anode. In anode means the positive electrode. Positive electrode means the electrode which is connected to positive terminal, and so this is anode, and this is cathode which is connected to negative terminal. In anode, oxidization occurs. Anode oxidization. Let's look at the oxidization reaction. H2O to H2O liquid forms O2 gas plus 4H plus aqueous and 4 electrons. And in cathode reduction reaction occurs. 4H plus 4 electron, they form 2H2 gas. If you consider the overall reaction is 2H2O liquid forms 2H2 gas plus O2 gas. If we look at the overall reaction, we can say that the H2O concentration does not affect the electrolysis. We can find the minimum voltage required for electrolysis of water using that E cell equal E cathode minus electrode potential of anode, using that equation. And anode oxidization occurs in H2O breaks into O2 and 4H plus. For that reaction, the electrode potential is 1.23 voltage. For formation of H plus, electrode potential is 0. Standard hydrogen electrode. This is standard hydrogen electrode. And if we consider those, here cathode is 0 voltage minus 1.23 voltage. Therefore, the E cell should be minimum voltage should be 1.23 voltage. When the E cell potential, when the potential of the cell is negative, if it's negative, delta G will be positive. External electrical supply should be minimum of 1.23 voltages. Now let's look at electrolysis of copper sulfate using copper electrodes. Electrolysis of copper sulfate using copper electrodes. This is used to purify copper. The raw copper is extracted from ore using carbon. However, there is many impurities. Therefore, the pure copper can be obtained when the copper sulfate solution is electrolyzed. Here the positive electrode will be impure copper and negative electrode will be pure copper. Let's write them down. Anode, which is positive terminal, positive electrode. Positive electrode is impure copper. And the cathode which is negative electrode, which is pure copper. And we know that in anode oxidation occurs, and in cathode reduction occurs in electrolysis. Impure copper rod will dissolve and provide copper 2 plus ions to the solution, and while the more copper solid will deposit on the pure copper and grow its size. The cathode size will grow. Let's look at the reactions. In anode reaction, let's look at the anode reaction. Anode reaction, copper solid will form Cu2 plus aqueous plus 2 electrons. Here the cathode, which reduction occurs, Cu2 plus aqueous plus 2 electrons, they form copper solid. Here oxidation occurs. Here in cathode reduction. Now let's look at the experimental setup of electrolysis of copper sulfate using copper rods, using copper electrodes. This is the experimental setup, and these are dipped in CuSO4 aqueous, and this is pure copper, and this is impure copper with impurity, and they are connected using a wire, and the positive terminal, and this is negative terminal. Positive terminal is anode and the negative terminal is cathode. Anode and this is cathode. The copper in the impure, they release into aqueous solution Cu2 plus, and these Cu2 plus will form attach, and this is the newly formed. This is copper depositions. Okay, the next part is electrolysis of copper sulfate using inert electrodes. Electrodes are inert electrodes. We use electrodes such as inert. In this case, we use inert electrodes. Inert electrodes are used. Example, we can take platinum and graphite. Now let's look at the reactions in anode and reaction in cathode. Here the anode release O2 gas. Anode releases O2 gas, and cathode deposition of O2 gas and deposition of copper. Copper deposition occurs in cathode. And now let's look at the reaction. Anode reaction, H2O liquid forms O2 gas plus H plus and electrons. If we balance these 4, and this should be 2, and this is aqueous. And if we take the cathode, reaction. Cathode will be the ions in the aqueous solution Cu2 plus aqueous plus the 2 electrons, and the copper solid will form. And the overall reaction is, take the overall reaction 2Cu2 plus aqueous plus 2H2O liquid forms 2 copper solid plus O2 gas plus OH plus aqueous. We can find the standard electrode potential using the table. Using the standard reaction potential table in the exams, they will give us the standard electron potential. Here, oxidation of water is more feasible than the oxidation of sulfates. Here, oxidation of water is more feasible than oxidation of sulfate ions. Therefore, at the anode, O2 gas will be released by oxidation of water. Let's write it down. Oxidation of water is more feasible than oxidation of sulfate ions. Therefore, O2 released by H2O. Oxidation of H2O. Now let's discuss about electrolysis of sodium chloride using inert electrodes. When considering electrolysis of sodium chloride solution, it is important to analyze the oxidation and reduction reaction that can happen in corresponding to the electrode first. And then the comparison of the standard reduction potential of the reactions can be used to predict the product. First, we should find the which electrode undergo oxidation and which electrode undergo reduction. By comparing them, we can predict the final product. Now let's look at the reactions of electrolysis of sodium chloride. First, H plus gas, H plus aqueous plus 2 electrons, they form H2 gas. Is 2, and the second reaction is 2H2O liquid plus 2 electrons and 2H2 gas, sorry, H2 gas plus 2 OH minus aqueous. The next one is Na plus aqueous plus electron forms Na solid. And if we consider the reduction potential of these, reduction potential of hydrogen is 0 voltage. Reduction potential of H2O is equal minus 0.83 voltage, minus 0.83 voltage. And the next one is equal minus 2.71 sodium voltage, 0.83 voltage minus. Okay, when we consider the standard reduction potential, the most probable reduction reaction is the first reaction, but the H plus concentration is very low. Therefore, it is not possible under laboratory conditions. And if we consider the third one, it is very large negative potential. Third one has a very large negative reduction potential. Therefore, we can guess that the most possible reduction reaction is the second one. I'll mark down. This is first reaction, second reaction, and the third reaction. Okay, let's look at these. Okay, let's write the reasons. First reaction. Okay, let's write these are reduction reactions. Possible reduction reaction. First reaction cannot occur due to low H plus concentration. The third cannot occur due to large negative reduction potential. Second one, more suitable. Now let's look at the oxidation reaction. We should determine the oxidation reaction. There are two oxidation reactions. Let's look at those. Okay, now let's look at the oxidation reaction. Possible oxidation reaction. The first one is first reaction Cl minus 2Cl minus aqueous and forms Cl2 gas and 2 electrons, and 2H2O liquid forms O2 gas plus 4H plus aqueous and plus 4 electrons. Let's consider this as fourth reaction and this as fifth reaction. Fifth reaction, we should consider the reduction potential. We should consider the reduction potential of these. Okay, reduction potential of reaction fourth and fifth. And reduction potential Cl2 gas plus 2 electrons, they form 2Cl minus aqueous. And the fifth reaction, this is fourth one, and fifth one, O2 gas plus 4H plus aqueous plus 4 electrons, they form 2H2O gas, the fifth one. And the reduction potential of fourth reaction is plus 1.36 voltage, and reduction potential of water is, the fifth reaction is plus 1.23 voltages. If we consider these two reactions, the fourth and fifth reaction, the fourth reaction is more feasible than fifth one. According to the reduction potential, most favorable oxidation state is fifth. However, when the experiment is conducted, gas evolved with Cl2 but not O2. It is something called as, the reason for this is something called as over potential. It is not in our syllabus. Let's look at it after writing notes. Let's write it down. Fourth reaction is more feasible than fifth. Therefore, according to the standard reduction potential, the four most favorable oxidation reaction is fifth one. If we compare these two, If we compare these two, the electrode potential, the reduction potential of the fourth reaction is higher than the reduction potential of fifth. Fourth reaction undergo reduction quickly, but here we need to find the which undergoes oxidization quickly. Therefore, the fifth reaction is more suitable. Okay, now let's look at what is overpotential. Due to overpotential, gas evolved is Cl2, not O2. This means the reaction, the fourth reaction is occurring here. This is because of the actual potential that need to be supplied for the reaction to take place is sometimes greater than the standard reduction potential. What is overpotential? Let's write it down. Actual potential needed to be actual potential needed to be supplied E supplied for the reaction to take place is sometimes greater than the standard potential. The detailed discussion of these is not in our syllabus. And in other words, we can say that standard reduction potential can be used to obtain minimum voltage values. Standard potential can be used to obtain minimum voltage values that can be supplied to drive an reaction of interest. Minimum voltage to drive the reaction. However, actual voltage may be higher due to presence of overpotentials. In this case, therefore, the Cl2 gas is released because the overpotential of reaction 5 releases O2 could be much greater than the reaction 4, and thus the reaction requires less potential to be supplied for the reaction 5. Therefore, the reaction 4 requires less potential to be supplied than the reaction 5. This is due to overpotential. Now let's look at the reactions here. Anode reaction undergo oxidization and the reaction is 2Cl minus aqueous forms Cl2 gas plus 2 electrons, and the cathode reaction is undergo reduction, and the reaction is 2H2O liquid plus 2 electrons. They form H2 gas plus 2 OH minus aqueous. The overall reaction is 2Cl minus aqueous plus 2H2O liquid forms Cl2 gas plus H2 gas plus 2 OH minus aqueous. And that's all for sodium chloride, electrolysis of sodium chloride using inert electrodes. Now let's look at electrolysis of sodium chloride, which is molten liquid sodium chloride, using inert electrodes. Now let's discuss about electrolysis of molten sodium chloride using inert electrodes. At room temperature, sodium chloride is solid and it does not have any mobile electron, therefore it does not conduct electricity. It does not conduct electricity. The solid sodium chloride does not conduct electricity due to absence of mobile ionic species. And when the temperature is raised beyond the melting point, the molten sodium chloride is produced, and it contains sodium plus ions and Cl minus ions. An electrolysis of molten sodium chloride will result reduction of Na plus ions to Na solid. And Cl2 gas is also produced as oxidation product. Let's write it down. For sodium chloride solid, heated, and sodium chloride liquid. And liquid contain Na plus ions plus Cl minus equals, and this Na plus electron forms Na solid, and this Cl2 minus 2Cl2 minus forms Cl2 gas plus 2 electrons. Here this is this one equation. This is cathode reduction occurs here, reduction, and this is anode, oxidization. And if we consider the overall reaction 2Cl minus aqueous plus 2 Na liquid, Na plus liquid, and they form Cl2 gas plus Na liquid. Sorry, this should be liquid, right? This is liquid, and this is also liquid. This is also liquid. Here Cl2 is also liquid. This is also liquid. This one is also liquid. Sorry about that. Industrially, sodium metal is extracted by electrolyzing molten sodium chloride solution. The industrial setup is known as down cell. They call it as down cell. Industrial Na metal is extracted by this method. They call this as down cell. They call this as down cell. Now let's discuss about quantitative aspects of electrolysis. The first scientist who described the quantitative aspects of electrolysis is Michael Faraday. There are two laws for electrolysis. There are two Faraday's law for electrolysis. Let's write it down. Faraday's laws by Michael Faraday. His first law was the amount of chemical reaction which occurs at any electrode during the electrolysis by a current is proportional to the quantities of electricity passed through the electrolyte, which can be a solution or melt state. Amount of chemical reaction which occurs at any electrode during the electrolysis by a current is proportional to the quantities of electricity passed through the electrolyte. Let's write it down in simple terms. First law. Amount of chemical reaction occurred is directly proportional to the quantity of electricity passed through electrolyte. The amount of chemical reaction occurred is directly proportional to the quantity of electricity passed through the electrolyte. Okay, the second law of Faraday is the amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. Let's write them in simple terms. Amount of different substances liberated. Amount of different substances liberated by same quantity of electricity passing through the electrolytic solution is directly proportional to their chemical equivalent weights. Their chemical equivalent weights. Their chemical equivalent weights. The first law is the amount of chemical reaction occurred is directly proportional to the quantity of electricity passed through the electrolyte. The second law, amount of different substances liberated by the same quantity of electricity passing through the electrolyte is directly proportional to the chemical equivalent weight. What is chemical equivalent weight? Chemical equivalent weight means AMU, atomic mass unit, divided by number of electrons required to reduce cathode. The quantity of electricity passed can be given as Q equal IT. Q means charge, I means current, T means time. The amount of current required for oxidation or reduction depends on the stoichiometry of electrode reaction. Let's write it down. Amount of electricity, or we can take it as charge needed for oxidation or reduction reactions depends on stoichiometry geometry of chemical reaction. The quantity of electricity is called as Faraday. Quantity of electricity is Faraday, which is a constant. It's a constant. And 1 Faraday is approximately equal to 1 Faraday, which is symbolized by capital F, is approximately equal to 96,500 coulombs per mole. For example, if we consider magnesium 2 plus, if we need to reduce this, we need 2 electrons and it will form a magnesium. Here we need 2 moles of electron. 2 moles of electron. To reduce magnesium 2 plus ion into F equal to F. Let's look at the application of Faraday's constant, and we multiply current, which is amperes, into time in second. It gives us coulombs, which is charge, coulombs C, and coulombs are converted into moles of electrons, and moles of electron, moles of product or reactants, product or reactants. Here we can multiply the current into time and find the charge, now amount of charge and amount of coulombs, and you can divide the coulombs by the moles and find the moles of the product and moles of the reactants. The last part is comparison. We already compared the galvanic cell and electrolytic cell. Let's look at it again. Here it is, galvanic cell and electrolytic cell. In galvanic cell, electricity is produced spontaneously, but in electrolytic cell, the electricity is produced non-spontaneously. Therefore, an external current should be supplied for electrolytic cell. And difference between anode and cathode, if we take the anode and cathode, both of them are anode undergo oxidation and cathode undergo reduction in both, but the terminals are different. Here in galvanic cell, the negative potential for anode and positive potential for cathode, and the movement of electron from anode to cathode. In electrolytic cell, anode is positive potential and cathode is negative potential. That's all for electrochemistry. I hope you guys understood. Thanks for watching.